If you've seen the movie Interstellar, and if you haven't, then I'd highly recommend it, then you'll be familiar with this shot. This is the supermassive black hole known in the movie as Gargantua. But you might notice it's not exactly black. I mean, yeah, the middle is, but what about all this light around it? You've got this bright band across the centre, and then this ring of light around the edge. So what's going on there? Well, the band across the black hole is in front of it. But all this stuff around the edge? Would you believe me if I said it was coming from behind the black hole? You may be wondering, how is this possible? How can we see stuff behind black holes? Well, I'm Thomas, this is Inversion Science, and you're watching How We Can See Behind Black Holes. Before I explain how we can see behind black holes, I first need to kind of cover what a black hole actually is, because calling it a hole isn't really accurate. A black hole is the end state of a massive star. Stars like our sun, when they die, will collapse down to be small balls of carbon and oxygen, known as a white dwarf. When you get stars a little larger than our sun, they can collapse down to become what are known as neutron stars, which are spheres of nothing but neutrons. But stars that are even larger than that when they die can collapse down even further. All of the mass that's left from the star is collapsed down beyond a neutron star into what we call a singularity, a single point where all the mass is concentrated. Because there is so much mass in the singularity, the gravity around it is extremely strong, so strong that there is a point after which not even light can escape. All bodies have what is known as an escape velocity. This is the speed you need to go at to escape their gravitational pull. Now, everything has this. It could be a black hole, a star, a planet, or even a human being. Escape velocity is given by this equation. In this equation, g is the universal gravitational constant, m is the mass of the body you're trying to get away from, and r is the distance you are away from it. To escape the gravity of a human being from a socially safe distance of 2 meters, you only need to move at a very, very, very minuscule 0.7 millimeters per second. To get away from planet Earth, you have to go a fair bit faster, at 11.5 kilometers per second. This kind of explains why we need massive rockets to go to space, but for a black hole, you have to go even faster. In fact, there's a point after which you can never escape, because the escape velocity becomes the speed of light. The radius from the black hole where this happens is known as the Schwarzschild radius, named after German physicist Karl Schwarzschild. The Schwarzschild radius is given by a rearrangement of the escape velocity equation. Set v escape equal to c, the speed of light, and then rearrange for r, where r is the Schwarzschild radius. This is the distance where we find the event horizon, the point after which you are never going to escape the black hole. So, if not even light can escape a black hole, how are we going to see behind one? Surely any light coming from directly behind the black hole will just be blocked. And to a certain extent, that is true. If a light beam is directly pointed at Earth and we put a black hole in the middle, it's never going to get to us, it will be swallowed, end of story. But what if that light is going to go past the black hole? Well, surely it'll never reach us. We're not along that path. This is where we need to consider one of the major theories of physics, Albert Einstein's general theory of relativity, proposed in 1915. What Einstein proposed was that the Newtonian laws of physics, which had been pretty good up to this point of explaining things on Earth and in the solar system, with the exception of Mercury's orbit, were wrong. Now, we still do use Newton's laws every day because on human scales, they're accurate enough to not cause a problem. But they're not good enough for massive scales. Einstein had already shown, using his special theory of relativity, that time is not constant. For observers moving at different speeds, time does not flow the same. Time is also changed by gravity. And space and time are inextricably linked by the laws of relativity. We get 4-dimensional space-time, where we link the 3 spatial dimensions, that's up and down, left and right, forward and back, with the 4th dimension, time. Einstein's general theory of relativity shows that gravity warps space-time, like putting a rock on a sheet of stretched rubber. Gravity creates what are known as potential wells, which can trap masses when they're not moving fast enough to escape, This is how we end up with orbits. We're actually in a gravitational potential well, or several right now. Earth creates a gravitational potential well, and we're gravitationally attracted to Earth, so we're in that well. But Earth orbits the Sun, so we're in that well as well. And the Sun orbits in a galaxy, so we're in the galaxy's potential well. It's a lot of wells. But everything we've talked about so far with respect to gravity has been matter. You could put it on scales if you had a large enough one, whether that be a person, a planet, or a star. It's all matter. But matter isn't the only thing affected by gravity. Energy is too. You're probably familiar with Einstein's mass energy equivalence, E equals mc squared. This shows that the laws of physics will affect matter the same way they affect energy. Now, light is made of photons, which are packets of energy, so they will also feel gravity's pull. To show how this lets us see behind black holes, we need to consider how objects move in 4D spacetime. For any photon or atom moving about in free space, that is, there's no forces, they'll always go in a straight line. Straight forwards. They follow what is known as a geodesic, which is the shortest path between 2 points. Now, we know that gravity warps spacetime, and to this photon that doesn't really do anything. But to an external observer, it looks like the path curves. This is actually how we end up with orbits, because matter just follows a straight line from its point of view, but a curve from ours. It is this path curving that lets us see behind black holes. If we want to change the path of light on Earth, without using a mirror, we use a lens. The lens causes the path to bend and focuses it on a single point. A massive object, like a black hole, will do something similar, creating what is called a gravitational lens. The light from behind the black hole is bent around it, creating what we call an Einstein ring. So, what are we seeing in the movie around Gargantua? Well, we see this band across the front of it, and we see this light around the edge. Now, the band across the front of it is clearly a disk. It's an accretion disk, made up of matter such as gas and dust, which has been caught in the gravity well of the black hole. It's orbiting round, and as it spirals in towards the black hole, frictional forces heat it up, causing it to glow, emit light, like any hot body does. In fact, it gets so hot that it emits X-rays, far more energetic than visible light. So if the accretion disk is emitting light, then that explains the bright band across the front. But what about the edge? Well, this is where gravitational lensing comes in. The disk goes all the way around the black hole. This makes sense, it's orbiting. But a gas particle, or a dust particle in the disk, will radiate in all directions. Some of the light will be fired towards the black hole, some will be fired towards us, and some will be fired tangential, that is to say parallel to the surface of, the event horizon. The black hole acts as a gravitational lens. Light from the far side of the accretion disk is bent round the black hole so we can see it. In fact, it can happen many times for light close to the black hole. This means that the bright light we see is simply from the far side of the accretion disk. This is what lets us see behind black holes, something as fundamental and everyday as gravity. So thanks for watching this video. If you enjoyed this and found it fascinating, then please subscribe for more like this. If you're looking for something else to watch, then I'd recommend my video on how physics made it easier to get to Mars. The blog post with all the sources I used to make this video is linked in the description below, and while some of them are online, I did use this book, The Science of Interstellar by Kip Thorne, quite a lot, so that won't be available online. While you're down there, if you have any comments, questions, criticisms, or ideas for future videos, then please comment below as well. But in the meantime, I've been Thomas, you've been watching Inversion Science, and I'll see you in the next video.